Okay, we're going to sort of finish up talking about empirical formulas and molecular formulas here. We're almost to the end of this conversation. Last time we were really getting into calculating empirical formulas. And when we calculate empirical formulas, which is the simplest formulas you could have, there's really several steps that you follow to do so. As we talked about, a lot of times you are given sort of the percent composition of all the elements that are present there by mass. And we usually just want to kind of convert those guys into grams. And really the simplest way to do that is just to assume that you have 100 grams of it, because again, it just keeps all the numbers the same. You can assume any number you want, but again, it just keeps all the numbers the same. Once we do that, really the next thing we want to do is take all those grams and convert them to moles. So obviously we use the molar mass to do that. Once we have that, we want to divide everybody by the smallest number of moles. And when we divide by the smallest number of moles, that will give us really numbers for each of the elements. And if those numbers do basically all hit whole numbers, are very, very close to whole numbers, then that would be your empirical formula. So again, if you get something like, 1.9899, somewhere in that ballpark, or a little bit above the number, you could round. We did talk about if you don't sort of hit a whole number, if you get something like we saw, like 0.5 or like a 0.33 on a number, those are some common ones that you sometimes come across. You do have to sort of figure out a factor to multiply the empirical formula by to get a whole number, and then that would give you obviously your empirical formula at that point. Any questions on that there? Okay. So we did an example there of calculating empirical formulas. We also did an example of a very common sort of procedure that's used to calculate empirical formulas, which is combustion analysis, where they basically do a combustion reaction. And when they do a combustion reaction, pretty much the products that you get in that situation are CO2 and water. And as we saw there, we could use the amount of CO2 collected to figure out the grams of carbon there were originally in the sample. We can also figure out the amount of our grams of hydrogen there were from the amount of water that's collected. And again, we take an organic guy basically, and we add some oxygen to it. The one thing that we can't figure out in this case, though, is the amount of oxygen directly from the water or the CO2, because we are adding oxygen in the process of doing this reaction. So obviously some of that oxygen gets into the water and some of that gets into CO2. But once we figure out the grams of carbon from the CO2 and the grams of hydrogen, since our organic guy here will basically be carbon, hydrogen, and oxygen, we will know how much carbon, we'll know how much hydrogen. So we could take the total sort of mass of the sample and subtract off the grams of carbon that was there and the grams of hydrogen that was there, and that would get us to the grams of oxygen that was there as well. At that point, in sort of a combustion analysis problem, it just sort of reverts back now to basically an empirical formula problem, where then we would take those grams, we could convert them into moles, divide by the smallest number of moles, and then get our empirical formula. So it's sort of a combustion analysis problem. There's just a little bit of work in the front part there to figure out the grams of everybody, and mainly also figure out the grams of oxygen in that part. Any questions on that stuff there? Okay. So we will then talk about how we get to the molecular formula. Remember, the molecular formula is the formula that basically tells you exactly what is present in that particular compound, the exact amount of, say carbons, hydrogens, whatever it may be. There's basically three things that you need to calculate a molecular formula. The first one is the empirical formula. So one of two situations occur when you have a problem like this. Either they will just straight out give you the empirical formula, or secondly, you will need to calculate the empirical formula like we've been doing. So a lot of times you do have to sort of calculate the empirical formula first and then kind of continue on. So However it is given to you, or you need to calculate it, you do need the empirical formula. The next thing that you need is the approximate mass of the compound. The approximate molar mass of the compound in textbook problems and most problems is usually given to you. So somewhere in the actual problem, they'll say, hey, this guy has a molar mass of like 120 grams per mole. They may even give you a range, like this guy has a molar mass that ranges somewhere between like 100 and 110 grams per mole. So it'll give you some type of information about the molar mass of the compound. The last thing that you need is basically the empirical formula's molar mass. So you should have the empirical formula at this point. You can get the molar mass of the empirical formula. And then basically what you do is you take the molar mass of the compound that was given to you in the problem, and you divide it by the molar mass of the empirical formula, and that's going to give you a number. And the one place where it's pretty safe to round is in this situation here. If even your number's a little bit not a whole number, you can round pretty safely in this case. And let's just say we did this, for example, and we had an empirical formula of A2, B4, something like that was our empirical formula. We did this and we got like a 2 as our number. We basically would then multiply the empirical formula by 2, and that would give us A4B8 as our molecular formula in this particular case. So whatever number you get, you basically will multiply your empirical formula by, and that will give you your molecular formula. And again, that's why in this case, it actually is safe to round, even if it's not perfectly a whole number, because it should be sort of a multiple whole number that you should have here. Any questions on that? Okay, so why don't we try one here and see. A sample of a compound contains hydrogen and boron. The molar mass of the compound is 30. What is the molecular formula? We'll give you some numbers here. Boron is, looks like 1081. And hydrogen is 1.008. All right, so calculating. So we are looking for the molecular formula, which means we obviously do need the empirical formula, which was not given to us. So that's really where we could start. We could just start with our basic sort of empirical formula calculation. So we have the grams of each of these. So we're going to take the grams here of boron. We're going to use the molar mass from the periodic table here to convert it into moles. We will also do the same thing for our hydrogen, using the molar mass there from the periodic table to convert it into moles. And looks like we will end up here with, call it 0.5961 moles of boron, and it's like 1.7887 moles of hydrogen. In this particular case, obviously, we're going to divide by the smallest. So that is boron in this case. So we're going to divide by boron here and give us 1. And if we do that there, I think it's a 3, if I'm not mistaken. That is a 3. In this case, we did hit whole numbers, so that would give us our empirical formula here of BH3 is our empirical formula. Any questions up to that point? At this point, we need 2 more things. One, which is already given to us, that the molar mass of the compound is about 30 grams. And then we need the molar mass of our empirical formula. So getting that would be 1081 plus 3 times 1.008 gets us 81 plus 3 times 1.08. Looks like a 13,834. So what we will do is take the molar mass that was given to us in the problem, which is the approximate molar mass there. We will divide it by our molar mass of our empirical formula, 13,834. And that is going to get us like a 2.17. Again, on this sort of guy, it is okay to round. So we'll call that a 2. which is the factor that we do need to multiply the empirical formula by, and that should get us something like a B2H6 as our molecular formula. Any question on any of those steps? And again, if you're wondering why it's sort of okay to round here, it is because a lot of times what you are given is sort of an approximate molar mass, so it's not like perfectly the exact molar mass of it. So there is going to be a little wiggle room in terms of when you divide it out and stuff like that. So that's why, even though it's a little higher than we kind of would do in the other situation, that's why it's okay to kind of round it to a whole number in that situation. Any questions on that? Okay, let's try another one here, I think. Yeah, let's do this one here. Phosphorus oxide contains 43.64% phosphorus, 5636 oxygen. What is the empirical and molecular formula here? Phosphorus is 3097. And oxygen is 16. Badly drawn 16 there, but a 16 would work. There we go. All right. Okay, so let's take a look. So in this case, we are looking for both formulas. So might as well start with the empirical. We are given the percentages of each of the elements. So we just want to quickly look at it again, make sure it does add up to about 100%, which it does. And again, if it doesn't, then clearly some elements missing there if it's not adding up to 100%. Since it does, we can just assume we have 100 grams of it like we've talked about. And again, that's going to just keep everybody the same numbers here. So that would mean we had 43.64 grams of phosphorus, which once again, we could convert into moles by using the molar mass from the periodic table, 3097 grams per mole, basically dividing by that. And that would give us 5636 there grams of oxygen, a little dividing action there by 16. Which is our moles there, our molar mass of oxygen. That gets us 4364 divided by 3097, going to give us a 1.4091 moles of phosphorus, and 5636 divided by 16 looks like a 3.5225 moles of oxygen. Once again, to calculate our empirical formula, we are going to divide by the smallest, which in this case looks like it is the phosphorus here. And that's going to give us a 1 for the phosphorus and basically a 2.5 there for our oxygen. This would give us an empirical formula, PO2.5. As we talked about, we cannot have really a decimal there. And that is, again, in the case of empirical formula, too far to round. So we're going to figure out a number to multiply the 2.5 by to get to a whole number, which clearly, if we take perhaps 2 there, would get us a 5. So that is the factor that we would want to multiply that by. And again, it's not just the oxygen, but we do need to multiply everybody by that too. So multiplying by 2 gives us the proper empirical formula, P2O5 in this case, which would be our empirical formula. Any questions up to there? At this point, we do have one of the things that we do need to calculate the molecular formula. The second thing that we need to calculate the molecular formula was given to us, which is the molar mass of the compound. So we do just need to actually get our empirical formula's molar mass. And that would be 2 times our 3097 for our phosphorus, plus looks like 5 times 16 there for our oxygen. That's going to give us a molar mass there of our empirical formula of, not that, try that again, 2 times 3097 plus 5 times 16. Looks like a 141.94 grams per mole. So to figure out the factor to get us to our molecular formula, we take the molar mass of the compound that's given to us, which is our 283.89. We divide it by our empirical formula's molar mass there of 141.94. And in this case, we do hit a 2, I want to say. About a 2. So that 2, once again, is what we need to multiply our empirical formula by, and that would get us something like a P4O10. First off, any questions on that? I personally kind of multiply out the numbers like that. Occasionally, you will see people kind of take the empirical formula and just kind of put a 2 on the bottom for the molecular formula, but I think it's better just to probably multiply it out in that particular case. Any questions on how to calculate the molecular formula here? So this is one approach, and it's a good approach. You probably won't screw up too much if you kind of go this way. You can, if you wanted to, sort of start with the molecular formula and kind of work your way backwards in a situation like this. Since you are given the percent composition by mass of each of the elements, and you do know the actual molar mass of the compound, you could actually go molecular formula first and work backwards. Just to show you how that would look, let me do here, I think. So we had okay, so if we have the same problem where, again, we had 43.64% phosphorus and our 56.36% oxygen, and the molar mass was 283, I believe, 89 grams per mole. Since you do have the percent composition of each of these elements and you do know the molar mass of the compound, you could actually just take the percent of phosphorus, for example, convert it into a decimal, which would be 4364, and you can multiply it by the molar mass of the entire compound here. And that basically will give you how many grams there are of phosphorus in the molecular formula, which would give you 283.89. And that's about 123.8895 grams of phosphorus. You could also do the same thing here with our oxygen. Convert the percentage into a decimal and times it by the molar mass of the entire compound. And if you do that, 0.5636 times 283.89 gets you about 160 grams of oxygen. Now that you have the grams of phosphorus and oxygen in the molecular formula, you basically can just convert those into moles by using the molar mass from the periodic table, which is our 3097 grams per mole, and our 160 grams of oxygen. And if we do that, we end up with 10, and we end up with 4, and that would give us our molecular formula in this case of P4O10, which is exactly what we got before. And since that's the molecular formula, it is 4 phosphorus for every 10 oxygen, and that is basically the same as 2 phosphorus for every 5 oxygen, which is what you would reduce it down to, and that would get you to P2O5 for your empirical formula. So you can work backwards if you want to do it that way. If you do have, again, the percentages and the molar mass of a compound, you can go molecular formula and just reduce it down to whole numbers to the empirical formula, or obviously you could go empirical to molecular formula. Any question on either way of doing that? All right. So I think what we will do is you have one more example there. So you can do that example. Let's see, where is that? What we're starting right now, not on the exam on Monday. This will be exam 3 material here. It's just a little back part, I think, of chapter 5, if I'm not mistaken, which is balancing equations. In this chapter is what we're going to talk about. We're also going to talk about different types of equations or reactions, different ways to classify reactions. So let's get into it. First off, obviously a chemical reaction is a process really where we have a chemical change occur, and a chemical change is what you start with and what you end with are fundamentally two different things. You can't really get it back through any type of physical means, which is like, boiling, melting, freezing, or filtering, or anything like that. And usually what we represent a chemical reaction with is a chemical equation, which obviously uses the symbols and the formulas on different sides of the arrows. Here's some different ways to represent equations. And on the left-hand side of the arrow, these are all our reactants. And those really are the starting materials in a chemical reaction. They're really the guys that pretty much are going to break all their bonds as they kind of progress through the reaction. And as they sort of reassemble those bonds on the other side of the arrow, if you want to think about it that way, those are our products. And our products obviously are sort of our new compounds or formulas, our molecules that are formed as a result of a chemical reaction. Some other things that we very commonly see in chemical equations is we see the states of everybody. So you will sometimes see solid written next to formulas, which means, or S written next to formulas, which means solid. You'll see L written, which means liquid. You'll see G written, which means that substance is in the gas state. And also very commonly, you will see aqueous written, or AQ written next to it, which is basically aqueous or a water environment. Now, sometimes people have a question of like, what is really the difference between aqueous and liquid? They're both really in the liquid state. They're both basically kind of liquids in that sense. There is a difference between them. When you see L, it is basically a pure substance by itself. So it's just a liquid by itself. So for example, if you just had water by itself, that would get a pure liquid sort of indication next to it. If you took something like a pure liquid like water and you added some solid sodium chloride to it, the sodium chloride or salt would dissolve in the water. And what you would be left with is a sodium chloride solution, which would get the aqueous symbol next to it. So aqueous is usually involved, really represents a solution, which really usually means you took something like a solvent like water, you put something in it, kind of mix it together, and it all mixed together in a homogeneous fashion, and everything looked really good. So there is a difference, even though they're both technically in the sort of liquid state. If something has a L next to it, it is sort of a pure substance in that sense. Other things that we also commonly see is sometimes we will see things on top of the arrow. Sometimes we'll see a little delta symbol, which oftentimes means heat. Sometimes people will write water up on the arrow, and that's usually a process where maybe we're dissolving something in water. A lot of times as well, on top of the arrow, we have catalysts written. So maybe you'll see something like, PT, like a metal catalyst. Maybe you'll see something like H+, which means there's an acid being used as sort of a catalyst that's written up there. A catalyst is not a reactant. It's not a product. It actually does not get used up in the reaction itself. It is there really just to facilitate the reaction occurring a lot faster in most cases. So a lot of times people will add a catalyst to a reaction to speed it up, but it actually does not per se take part in the reaction as like a reactant or product, and that's why it's still there usually at the end. Sometimes a catalyst is something as simple as, it's like a metal where everybody's attracted to that central location, allows the reaction to sort of take place a lot faster than it would if everybody has to kind of fly around and find each other. So that's very common. Usually we will use a chemical equation to represent a chemical reaction, but we can use chemical equations to represent physical type of changes that occurs as well. So for example, if we had something like water in the solid state going to water in the liquid state, that is technically not a chemical change or anything like that. That is a physical change, but we do sometimes use chemical equations to represent physical changes that occur as well. That's obviously like ice melting, basically the liquid water. Any questions on that there? So we can read this reaction, and it's going to be important a little bit later on when we talk about stoichiometry, but we can take these coefficients here in this balanced equation, and we can say 2 atoms of magnesium react with 1 molecule of O2 to make 2 formula units of magnesium oxide molecule, because O2 is covalent, so it's a molecule. Sometimes for ionic compounds, they're referred to as formula units because they're ionic. They're not technically sharing electrons and stuff like that. This relationship, as you might be familiar with, and we definitely will see in a little bit in a different chapter here, that's really what's referred to as the mole-to-mole relationship when we look at an equation, and it does come from just the coefficients from the balanced equation. So we could say there are 2 moles of magnesium react with 1 mole of oxygen to give you 2 moles of magnesium oxide. Conservation of mass, right? We have basically 80 grams of reactants, and because really the only thing that happens in a chemical reaction is all these guys break their bonds, and pretty much all these guys make new bonds, we should still have the same number of magnesium oxygens on both sides, so we have the same molar mass for all those guys on each side, and that's our conservation of energy, conservation of mass. We do not look at the coefficients as grams, so we don't do that in terms of that. All right, we'll get back to that obviously a little bit later on when we are talking about stoichiometry. So we're going to talk about, again, the steps to balance a chemical equation. And really the first thing you want to do is you want to make sure that you do write all the formulas correctly. So sometimes people, when they are going to balance equations, do 2 things that are really bad, or one thing I guess is really bad, is they try to write formulas and also balance the equation at the same time. And it's common in 2 ways. Most commonly it happens when you have the reactants and you like has to predict what's on the product side. So people try to like balance the equation and write the formulas. And usually what happens in that situation is you end up with the wrong formula, and that equation will never ever balance because you're not starting with the right formulas. So it's really important to do it in sort of 2 steps. You want to always make sure you got all the correct formulas down, regardless of the balancing aspect of it, even if it's unbalanced to begin with, and that's perfectly fine. And then you want to go back and balance. You, again, do not want to kind of do those 2 things at the same time. If you're given everything in words, just like a nomenclature, you again want to just make sure you get down all the correct formulas along the way. So something like this, where we have ethane reacts with oxygen to form carbon dioxide and water, we could translate that into our unbalanced equation here of C2H6 plus O2 gives us CO2 plus water. Another really important thing to remember is those diatomic molecules and elements. So things like oxygen, nitrogen, you know, those guys, they come as 2. So a very common mistake, people like, for example, here would just write O for oxygen, right, instead of O2, or H for hydrogen instead of H2. So oxygen, just like that, sometimes it's referred to as molecular oxygen. Molecular hydrogen means H2, O2, hydrogen gas, oxygen gas. So those are 2 very common mistakes. Once we have this, this is our unbalanced equation. And really here, I'm just going to rewrite it so we got a little bit more room between everybody. I personally think, and if you want to do this, it's sometimes helpful to make sort of a table of all the elements that you got going on there. So we really have sort of a reactant side and a product side, and we have carbon, hydrogen, and oxygen in this case. On the left-hand side, we can see we have 2 carbons. Right-hand side, we have 1 carbon. Left-hand side, we have 6 hydrogens. Right-hand side, we have 2. Left-hand side, we have 2 oxygens, and right-hand side, we actually have 3 oxygens, 2 there and 1 there, gives us 3. So if you want to use a table like this, sometimes it's helpful just to kind of organize everything, and also kind of gives you a good idea maybe where you might want to begin along the way. When we balance equations, the only thing that we change is the coefficient, and that is the numbers that come in front of all the formulas. You should never, ever change any of the subscripts, because if you change those small guys, then you're obviously changing what it is. Should also not do any weird things that I've seen before, like put big numbers in between elements, like a big 2 or something in between those things. So only the numbers in front. So in this particular case, I'm going to personally start with carbon because it seems like it's not too bad of an idea here. I have 2 carbons on the left. I got 1 on the right, so I can fix the guy on the right there by just putting a 2 in front of it. When I do that, that is now going to give me 2 carbons. I will still have 2 hydrogens. Now my oxygens is 2 times 2, which is 4 in the first one, plus the 1 more over here gives me 5 total oxygens in this case. At this point, I have fixed the carbon. I'm still in a little trouble here on some of the other things. I could clearly look at this and see that hydrogen probably is the easiest to fix. Oxygen on the right-hand side is in a couple of things, so that's not going to be so easy to fix. So hydrogen, we could kind of do a one and done situation probably. We could fix that by putting a 3 on the right-hand side. Again, the coefficient there. That's going to give us 2 carbons. 3 times 2 is 6 hydrogens. Now, in terms of my oxygen, I am up to 4 on the first guy and 3 on the second guy. That is 7 in this case. So now that we're putting coefficients in here, there's a couple of things that you do want to make sure of when you are done balancing an equation. And one of those things is when you are all said and done, you obviously need to have all whole numbers as your coefficients. And they do need to be the simplest set of whole numbers. So what I mean by that is, let's just say we had an equation where you balanced it with a 2 for that guy and a 4 for that guy, and we'll just say it's balanced. Obviously, it's balanced, but we can look at the coefficients here and reduce it down, right, by 2. So we would want to reduce it down to A and to B, and that would be the properly balanced equation. So this happens a lot. Sometimes people see larger numbers to balance it, and you definitely can balance it with larger numbers sometimes. But if you have the ability to go through all the coefficients and reduce them down and still keep them as whole numbers, then that is the proper balanced equation when you reduce it down. So in this particular case, when we look at this, we pretty much have fixed the carbons, we fixed the hydrogens. We pretty much got nowhere to go on the right-hand side, and we don't want to change those because obviously that's going to change the carbons and the hydrogens. So we really need to come over here to the left-hand side and balance the oxygen. In this case, we need to actually turn a 2 into a 7. And the way you could do that sometimes is by using actually a fraction to do that. Up on top is the number we need, which is 7. Up on the bottom, or down on the bottom, is the number that matches this guy. And that is because now if I look at it, I have 2 carbons, I have 6 hydrogens, and 7/2 times 2 is 7 oxygens in this particular case. At this particular point, my equation is balanced, but is it a properly balanced equation at this point? It is not, because again, I have a fraction basically. I don't have a whole number. So this illustrates a good point that you can use a fraction to balance it, and oftentimes happens like this where you got elements in a couple places on the right and maybe by itself and is on the left. But you do need to clear the fraction when it's all said and done. So to clear the fraction here, what we would want to do is multiply not just the fraction, but the entire equation by the denominator, I think they call that these days still. So if we do that, that would get us 2 of the C2H6 plus 7 of the O2 goes to 4 of the CO2 plus 6 of the H2O. And if we did this correctly, we should still be balanced here. That's going to be 4 carbons on the left and 4 on the right. That's going to be 2 times 6 is 12 hydrogens on the left. 6 times 2 is 12 on the right. And in terms of oxygen, 7 times 2 is 14. And we have 8 in the first one and 6 in the second one, which I hope is still 14. And this would be our properly balanced equation. So most people do a trial